Hello and welcome back. We are 3 weeks away, 3 or 4 weeks away from before this end of the school year. We have almost made it. Uh, it is currently Revenge of the Fifth. So please get out your Star Wars regalia, and we will get started. So this week, what we are talking about, we're going to shift a little bit away from concentration, dilutions, just very, very slightly. Not that we're not going to use that, but we're going to be using it inside a context of something else. So, what we're moving to slightly is called colligative properties. Now, colligative properties are properties that depend on the concentration of solute particles, but not on their identity. So the technical definition for colligative properties saying something that it cares about how or where you are, but doesn't care about how it got there or why it's there. So it's kind of like if you're at the top of the mountain. No one cares how you got to the top of the mountain, other than the fact that you're there. You could have climbed it, you could have skydived down from a plane. It doesn't matter. You're at the top of a mountain. That's what we're talking about. So, there's three different colligative properties that we're going to learn about, two of which we're going to study in depth, one of which we're just going to mention right now as we go. So, that colligative property is called vapor pressure lowering. So, vapor pressure is the amount of water molecules that uh, evaporate. So at certain pressures, water evaporates easier or quicker, and then at other pressures they go slower. So there's vapor pressure lowering, which happens when you use different solutions. That's all you really need to know about that. What we're going to focus on today is we're going to focus on freezing point depression. So, freezing point depression is the difference between the freezing points of the pure solvent and a solution, and is directly proportional to the mole concentration of the solution. Now, I know a couple of you are thinking, why did we have to do molality? We had molarity, it was perfectly fine. Molality is just this weird thing. I mean, molarity is weird too, but at least we knew that one. Why do we have to have two? We had to have two because molality is what we use for when we're doing freezing point depression. So, what this basically means is anytime you have any kind of solution, so it could be, say, salt water, could be sugar water, literally any kind of solution, not mixture, solution, you're going to actually lower the freezing point of a specific substance. So think about it. For the winter, when we want to make sure that the roads aren't going to get slippery with ice, what do we do to prepare the roads for an ice storm? We put down salt. That salt makes a solution with the snow as it's falling, and that solution actually melts. It lowers the melting point to the point where the ice or the snow or whatever it is doesn't actually freeze. It actually just melts. So that's what low freezing point depression actually is. So this is what freezing point depression looks like. So we have the pure sample uh, of water. This is where water is a liquid and solid and gas. What happens is when you make a solution with it, it actually lowers it a certain amount, which allows us to, say, melt ice, melt the ice off the road. This is why when it gets cold enough, so I believe not this past winter, definitely not this past winter, but 2 years before, there was a big ice storm, and they tried to salt everything to help, but it was so cold that the salt actually didn't work. The salt was actually ineffective because it was so cold, it was still being in its solid form. So salt doesn't necessarily melt ice, it just lowers the freezing point depression. So that's a little fun fact about without the rock salt that you use to melt the ice off your driveways. So through experimentation, the freezing point of a 1 molal solution of any non-electrolyte solution in water was found to be 1.86 degrees Celsius lower than the freezing point of water. Basically, that's a fancy way of telling you, hey, we have a we have a constant for the freezing point of water, and that constant is 1.86 degrees Celsius per meter, per molal concentration. I don't know why I said meter, please ignore that. So, this is only the value for water. Now, if there's ever a time when you're working with something that is not water, you're going to be either given this concentration, this constant, or you'll be given everything else and asked to find this constant. So, in general, you should know that the molal freezing point constant for water is 1.86 degrees Celsius per molality. Now, typically this number will be given to you. It should be given to you on all your homeworks. Make sure you have it written down. Make sure you have it with you so you know what's going on. Like I said, if you're given something besides water, this point will change. But you'll either be given the new one or you'll be asked to find the new one. So don't be too stressed out about it. So freezing point depression can be calculated using this depression following this formula. So we have delta TF is equal to KF MI. So we have delta. What's delta mean? Change. So delta is change. So delta T. T is going to be our temperature. So it's going to be the change of temperature of the F, or the freezing point. So we have the change of the freezing point temperature is equal to Kf, which is the freezing point depression constant. That's going to be the constant that is for our solvent. So for the solvent of water, we just learned that it was actually 1.86. That's written right here again. So for Kf, for water, we have 1.86 constant. That's always going to be there. Now, don't forget your units of degrees Celsius per molality. So we have the change in the freezing point temperature is equal to this freezing point depression constant times the molality of the solution times I, which if we look down here, I is the Van Hoff's constant. Now, Van Hoff was a German scientist, I want to say, either German or Swedish. And he discovered this constant. So we're going to talk about what that is in just a moment. So stick with me. But each one of these things is something that you should be able to find. So freezing point depression, temperature, the change in temperature of the freezing point depression. Now I want to bring this up as a very important point. This is not what the temperature is by itself. This is the change. So for water, we have to think what the actual freezing point is. The actual freezing point of water, of the pure substance of water, is 0, right? So since it's 0, whatever we get here is we're going to take that and add it to 0. So if we get negative 50, then we're going to go ahead and just say that the freezing point of water of that solution is going to be negative 50 degrees Celsius. And that's all it is. That's all it takes. But we have to be careful of this because the next colligative properties can be very similar, but instead we're going to be adding to what was there instead. Well, we'll get to that next week. So, the Van Hoff's constant, what we just talked about, what the I is. The Van Hoff's constant is very is very simple once you realize what it is. So we're going to give you some examples right here. We have sugar, which is C6H12O6, gives you a Van Hoff's constant of 1. Sodium chloride gives you a Van Hoff's constant of 2. Magnesium chloride gives you a Van Hoff's constant of 3. And aluminum chloride gives you a Van Hoff's constant of 4. Now, where do you think we're getting these numbers? Now, I know some of you are going to be saying, well, it's the number of atoms in the thing. Well, you're right, except for this first one here, right? Because we look, there's 1, 2 in sodium chloride. Well, there's 2. Okay. Magnesium is 1, 2, 3. 3. Okay. Aluminum chloride, 1, 2, 3, 4. 1, 2, 3, 4. That's, well, it's the number of atoms, except for up here. If we followed that for sugar, it should be 6 plus 6 plus 12 is 24. But it's 1. The reason that it's 1, has anyone spotted the difference yet? Sugar is a covalent bond. So anything that has a covalent bond, which is a non-metal and a non-metal, we cannot forget these things that we already learned. Because this is a covalent bond, which is a non-metal and a non-metal, its Van Hoff's constant is always going to be 1 because it doesn't dissociate in water. It's not going to break apart. So where do we get these values? So ionic compounds don't just dissolve in water. So there's a difference between what ionic compounds do and what covalent compounds do. So ionic compounds actually dissociate in water. So what's dissociate mean? Okay, that's a fair question. Think. Disassociate means that they're distancing themselves from each other. So what happens in ionic compounds is when they are put into water, they break apart into their individual ions because their bonds are so weak with each other because they just steal electrons, right? Their bonds are so weak that they actually break apart really easily when they're put into something as trivial as water. So when you break apart these individual ions, say for NaCl, you end up with Na plus and Cl minus. And then all you gotta do is add up how many things broke apart. So we have 1, 2, giving you 2. For AlCl3, aluminum chloride, you have aluminum 3 plus 3 Cl minus. So 1 plus 3, 4. Now, not all ionic compounds will dissociate in water. We're not going to say that as a blanket statement, but most everything that is an ionic compound that you would encounter in the real world will dissociate in water. So it's better to just assume that it will and then roll back as you meet the individual um, exceptions to the rule. So this is when knowing our ionic compounds and our covalent compounds comes into play. We spent a lot of time on this in the fall, so please let's make sure that we can remember it. If you need a refresher, I highly encourage you to look through your old notes or anything like that. The basics of it is if it's a nonmetal and a nonmetal, it's a covalent bond. If it's a nonmetal and a metal, it's going to be an ionic bond. That's pretty self-explanatory. Should be pretty easy to find. So that is actually it for the week. So we're going to be working with freezing point depression as we go through this week. Also a little bit about colligative properties, what they actually are. That should be the work that you go through for the next 2 days. Once that just looking forward in the future, we have next week we're going to be dealing with boiling point elevation, which is very, very similar to this. Almost no difference at all if we're going to be talking about it in all honesty. And then the last week we will be dealing with probably the last week of our instruction. So we'll have this week, next week, and then the week after will be probably the last week of actual instruction for this class. We have almost made it. If you haven't finished up your work, please make sure that you're finishing your work on time on Monday by noon. And please make sure that if you have any questions, you email me or join the office hours on Thursday. So until we see each other again, stay safe.